So this is, what is the terminal? Drain, source, and this is N-type. Lightly doped, plus indicates that P regions are heavily doped, and these two P regions are tied together, and a common terminal is taken out, that is gate. So we know very well, we have revised many times the constructional details, and the biasing drain and source, whether it is a P-type or whether it is an N-type channel or P-type channel, always charge carriers has to move from source to drain. They will move from source to drain. Accordingly, we need to provide the biasing between the drain and source. So suppose if it is N-type, the majority electrons should move from source to drain. Therefore, the drain must be provided with a positive potential compared with the source. So this is the connection we need to provide between the drain and source. This is the biasing voltage we need to provide between drain and source, so that the majority charge carriers will be drifted towards the drain. And in FET, gate and source junction, the junction which exists between the gate and source, there exist two junctions in the FET. So between the P plus gate and the N-type channel. So now if you observe the junction between the gate and source, always it must be reverse biased. So P plus gate must be connected to the negative terminal and positive terminal is connected to the source. So this is VGS. Always gate, the junctions, gate source junctions, always they must be reverse biased. So here whatever the biasing you are going to provide between gate and source terminals, biasing is to be given such that the junction must be reverse biased. And here whatever the biasing to be provided between the drain and source, it is to be given such that the majority charge carriers move from source to drain. So these are the, if it is a P-type P-channel JFET, then the biasing will be reversed, exactly reversed. If you simply reverse the polarities of VGS and VDS, then that will be applicable for P-channel JFET. That will be applicable for P-channel JFET. This is N-channel JFET. Okay. Now we will see the working of JFET. So just now we have seen that if you look at here, the drain current, it is the current generated due to the movement of charge carriers from source to drain. So when electrons are moving from source to drain, the drain current will be opposite to the direction of electron current, because the current direction in any electronic device, the conventional current direction is always the direction of the whole movement. That is, it is opposite to the direction of the electron movement. So this is the drain current. And if you observe, drain current is a function of, drain current will be controlled by two voltages, VDS and VGS. How they will control the drain current means, Just for an example, I'm saying to justify the statement what I have written here, this statement. Suppose if I increase the reverse bias voltage VGS, what will happen? Whenever reverse bias voltage increases, depletion width across the junction increases. So depletion regions, width of the depletion regions are going to increase when you increase VGS. So if depletion width increases, then the channel width is going to change. So therefore, with VGS, width of the channel will be altered. Width of the channel is altered. So when width is changing, then drain current also changes. So like that, VGS will control the drain current. Now coming to VDS. So when if VDS is increased, then number of charge carriers flowing from source to drain, number of charge carriers flowing from source to drain increases. So like that, both VGS and VDS will control the drain current. So we will see the working, how VDS and VGS will control the drain current. So that can be easily understood with the help of these diagrams. So we were discussing in the previous class. All of you see here, this is the case. So first case, this is not. So case 1, I'll write here case 1, VGS equal to 0 and VDS equal to 0. So when VDS equal to 0, if there is some potential at the drain, if there exists some potential at the drain, then only the charge carriers will be moving from source to drain. Then only the charge carriers will be moving from source to drain. When there is no potential, the current is 0. So when VGS equal to 0 and VDS equal to 0, then drain current ID will be 0. And the second case, this is the diagram figure A. We will talk about VGS is 0. VGS is 0. And we started increasing VDS from 0. So VDS is a small positive. It is a small positive. So when there is a positive potential at the drain end, the charge carrier starts flowing from source towards the drain end. And here, if you observe, VGS equal to 0. So when VGS equal to 0, the width of the channel is going to be constant because no reverse bias given externally. So channel width remains the same. Therefore, the channel acts like a constant resistor. The channel resistance is constant. We can say that when VGS equal to 0, channel resistance is constant. So we say that the resistance offered by the channel is constant. So channel resistance is constant. Therefore, the drain current versus VDS follows a linear straight line. So the relation between ID and VDS is going to be a straight linear. So ID increases with VDS. ID starts increases with VDS. And listen, whatever the depletion regions One second. So whatever the depletion region it is showing here, this is the depletion region formed at the time of construction. So during construction, when PN junctions are formed, around that junction depletion layers are formed. So these are the widths of the depletion regions are the widths at the time of construction. So there is no change there is no change in the width of the depletion region when VGS equal to 0. Therefore, the channel width remains constant and the channel almost acts like a increases linearly with VDS. Now coming to the third case. Assuming that VDS is a small positive quantity, now in addition to VDS, whatever the small positive voltage we have applied in the previous class, assume that the same positive voltage, the same small VDS voltages we have applied. Now, in addition to VDS, in addition to the drain potential VDS, we have also applied some external negative voltage to the gate. So when you give a negative voltage to gate, the negative voltage given to the PN junctions makes the junctions reverse biased. So when you provide, if you recollect, just now we have seen that the negative voltage in N channel JFET, when you provide a negative voltage, the gate source junctions will become reverse biased. Therefore, here, in addition to the drain potential, as negative voltage is applied on the gate terminal. So, VGS, we have given some negative voltage. So, since we have given the negative voltage, the reverse bias voltage, it makes the two junctions reverse biased. Therefore, we know that in reverse bias, the width of the depletion region is going to increase. This is the width of the depletion region. See here in the first case, figure A, this is the width of the depletion region under no reverse bias given to the gate. And in the second case, when you give some reverse bias voltage, width of the depletion region is going to increase. So these are the two depletion regions which are widened. So depletion regions are now widened. So since depletion regions are widened, what about the channel width? Is it same as the previous case? Or is it changed? Anyone? This is very, very important for direct.
Width decreases.
10 marks. Yes, very good. So width of the channel decreases. Now here in the second case, I will write here the channel resistance increases. Channel resistance increases. So, channel resistance increases. We know that resistance slope of a VI curve slope of the VI curve is 1 by the resistance. 1 by resistance. We have already discussed how to find the resistance from the slope. Is it right? If you take the VI characteristic curve, indicate 2 points. So this difference will give you the delta V, and the corresponding V by delta I is the resistance. So 1 by resistance will give you the slope. Now here in this case, width of the channel width reduced. So channel width reduces means the number of electrons, the rate of flow of electrons decreases. The rate of flow of electrons starts decreasing. Or in terms of the channel resistance, you can say that when depletion regions are widened due to the reverse bias voltage applied on the gate, the channel decreases, the slope of the VI curve decreases. So that is why if you observe carefully, if you assume that this is the IV curve when Vg is equal to 0, the slope is going to decrease. Therefore, this is the current variation with voltage when some negative voltage is applied on the gate. So it indicates that number of electrons for unit time decreases. Number of electrons per unit time is more in the first case. Number of electrons flowing per unit time is more in the first case. Whereas here, number of electrons flowing per unit time is reduced because of the reduced channel width. So therefore, the drain current and drain voltage, ID versus VDS curve, look at, one second, yes. So this is the curve when Vg is equal to -1. Now assume that we have further increased the negative voltage. Assume that we have further increased negative voltage. Further increased. So assume that VGS is increased further such that the two depletion regions will come in contact. The two depletion regions will come in contact. Now, can anyone tell what about the channel width?
Disappears.
Yes. Now, there is no channel at all. There is no path for the charge carriers to move from source to drain. There is no path for the charge carriers to move from source to drain. So therefore, drain current is going to be 0. If you observe, see here, this is the first curve where the current increases linearly. And when you start giving some negative voltage on the gate, the slope of the characteristic curve is going to decrease. That is, rate of flow of the charge carriers decreases. So, and when you give a more negative voltage, at one particular negative voltage, both the depletion regions will come in contact, and there will not be any path from source to drain. So this depletion region isolates or separates source and drain. So there is no movement of charge carriers from source to drain. That is why even if you observe the third curve, even if you increase the VDS, current is going to be 0 only. Current is going to be 0 only. So now here we will define an important term called pinch off voltage. We'll define an important term called pinch off voltage, which is represented as Vp. Okay. See here. So if you observe here, for the third case, so if you observe here, the reverse biased gate to channel space charge region has completely filled the channel region. It has completely filled the channel region. Is it right? I will underline here. The reverse biased gate to channel space charge region is nothing but the depletion region, has completely filled the channel region. So this condition is known as pinch off. So the condition when the depletion region is completely filled, the channel is completely filled by the depletion region, is called pinch off. So the drain current at pinch off is essentially zero, because depletion region isolates the source and drain terminals. Depletion region isolates the source and drain terminals. So channel has been occupied by depletion region. Channel is completely filled by depletion regions. And that condition is called as pinch off condition. And at the condition of pinch off, since there is no path from source to drain, drain current is zero. ID is zero. So we say that the third figure, if you observe, if you observe, for a negative voltage of minus V2, depletion region is completely filled and there is no channel at all. So drain current is zero. So this third curve, for minus V2, drain even if you increase this VDS from 0 to 0.1 to 3, there is no current at all. So that condition is called pinch off. So this is how the gate voltage controls the drain current. This is how the gate voltage controls the drain current. We will quickly revise. When there is no voltage on the gate and drain, there are no charge carriers which will be moving from source to drain because the drain potential is zero. So current is almost zero. Now, when you give some drain potential, at the drain, that too positive potential, అంటే ఎన్ ఛానల్లో మీరు పాజిటివ్ పొటెన్షియల్ ఇస్తేనే ఎలక్ట్రాన్స్ డ్రైన్ వైపుకి మూవ్ అవుతాయి. సో వెన్ యూ గివ్ సమ్ స్మాల్ పాజిటివ్ పొటెన్షియల్ with VGS 0, small number of charge carriers starts flowing from source to drain, resulting into a current called a drain current. So this is the direction of the drain current. So since there is no change in the width of the depletion regions, the channel width remains the same. Channel width is same. Therefore channel resistance is also same. So resistance rho into L by A, if you observe, so cross sectional area of the channel, length of the channel, all are same, constant only, because the depletion widths are not changed. So therefore when VGS equal to 0, channel width is same and the channel resistance is constant. Therefore, drain current and drain source voltage, they will follow Ohm's law. Current increases linearly with VDS. Now, as soon as you start giving this, see this case. So as soon as you start giving a negative voltage on the gate, this negative voltage makes the junctions reverse biased. So when reverse bias is applied, depletion regions are going to be widened. So when there is when the depletion regions are widened, channel width is decreased. Channel width is decreased. So the channel resistance of the resistance of the channel increases. Therefore, when channel resistance increases, the rate of flow of the electrons, the rate of flow of electrons decreases. Rate of flow of electrons decreases. So therefore, this is the curve. The slope with a less, the slope of the second curve is less compared with the slope of the first curve, because resistance and slope are inversely related. Since the channel resistance, because it is not allowing more number of charge carriers per unit time to flow, so therefore rate of flow is reduced. So therefore channel resistance is increased, slope is decreased. Andukani meeku curve, it will be bending below that. And if you further increase the negative voltage on the gate, if you continue to apply negative voltage on the gate, at certain negative voltage, the channel is completely filled by the depletion regions, and source and drain are completely separated by this depletion region. So there is no path from the charge carriers to move from source to drain, even though there is some positive potential. Even though there is a positive potential at the drain, no charge carrier will be moving, no charge carriers will be reaching the drain. సో మీరు VDS ఎంత ఇంక్రీజ్ చేసినా జీరో నుంచి డ్రైన్ కరెంట్ మాత్రం జీరోనే ఉంటుంది. సో ఈవెన్ ఇఫ్ యూ అప్లై ఎనీ పాజిటివ్ పొటెన్షియల్ ఎట్ ది డ్రైన్, current is zero. So this condition is called pinch off. Now similar kind of explanation we will see for VDS. So here we in this situation, in these figures, in these three figures, it is showing how the gate voltage is controlling the drain current. It is showing how gate voltage is controlling the drain current. Now we will see how drain current, how drain voltage, how this drain voltage is controlled, how this drain voltage is controlling the drain current. Now let us say, we all know that when VG is equal to 0, when VD is equal to 0, ID equal to 0. So remember, unless there is a positive potential in the drain, మీరు గేట్ దగ్గర ఎంత నెగిటివ్, ఎంత వోల్టేజ్ అప్లై చేసినా కూడా డ్రైన్ దగ్గర పొటెన్షియల్ లేకపోతే ఛార్జ్ క్యారియర్స్ సోర్స్ నుంచి డ్రైన్కి రావు. సో వాట్ ఎవర్ ఈస్ ది irrespective of the gate voltage, irrespective of gate voltage, irrespective of this voltage, if VDS equal to 0, ID will be obviously 0. So VGS 0 ఉంది, VDS రెండు 0 ఉన్నప్పుడు drain current is 0. Now first case, second case. Let us assume that a small positive voltage, see here, all of you see here, in these three figures, now we are trying to see, the effect of VDS on ID. Effect of VDS on ID. See here, a small positive voltage applied. In the second case, that positive voltage is further increased. In the third case, if you observe, a large positive voltage is applied. So we are observing the variation in the drain current when this VDS is increased from 0 to a positive potential, smaller voltage, further positive potential if you apply, how drain current is going to change. Okay. Now VDS is a small positive voltage is applied. VGS 0. Therefore, these are the widths of the depletion regions which are formed initially at the time of construction. Therefore, the charge carrier starts flowing from source to drain, resulting into a current called drain current ID. So current, as I said, current increases linearly with VDS because channel width is not changing here. Width of the channel is not changing here. So channel, it acts like a constant resistance. So therefore, current increases linearly with VDS. Now, second case, if you observe, when the positive potential on the drain is increased, when the positive potential on the drain is increased, here you need to concentrate carefully. Just a minute. Okay. So all of you please observe. Let us say we have given 4 volts plus 4 volts we have applied. So now what will happen? So what is the potential at the source? 0. The potential at the drain plus 4 volts. Now, let us, if you indicate some points, 1, 2, 3, so from here, from source to this point, let us say 1 volt. From source to this point, let us say the potential drop is 2 volts. From source to this point, the potential drop at this point with respect to source is 3. And the source to drain, what is the voltage? 4 volts. Now, what will happen? Otherwise, I can draw here. Okay, so here I have applied 4 volts with respect to the source. So when the charge carriers are moving, so we say that the potential difference between drain and source, the potential difference between drain and source is 4 volts. So drain is at plus 4 volts. drain is at plus 4 volts with respect to source. It means if you observe here at this point, the potential at this point with respect to source could be 3 volts. If you observe here, the potential at this point with respect to source is 2 volts, so 1 volt. So like that, the potential drop will be developed along the length of the channel. When charge carriers are moving from source to drain, I will repeat the sentence, remember. When charge carriers are moving from source to drain current starts flowing. So this when the charge carriers are moving from source to drain current will be flowing through the channel, and this current will develop a potential drop along the length of the channel. It will develop the potential drop along the length of the channel. And I have represented a few points along the length of the channel. I indicated a few points. At this point, the potential is 1 volt. At this point, the potential is 2 volts. At this point, the potential is 3 volts with respect to the source. Now, VGS is 0. VGS is 0. In all the cases, just we are observing the effect of VDS on ID. So we are set, there is no voltage on gate, so VGS equal to 0. Now see here, on both sides of the junction, if you observe, the P-type gate is at 0 potential, and N-type channel, if you observe, N-type channel, P-type gate is at 0 potential. First point is that the P-type gate is at 0 potential. And on the N side, if you observe, this entire region is N-type only, N-type. So the N-type channel, if you observe, everywhere the potential drop in the N-type channel is +1 to +3, +2, like that. So what I would like to say is, if a PN junction is there, and if P side is at 0, and on N side if it is greater than 0 volts, then we say that it is in reverse bias. I will repeat. If a PN junction is there, P is connected to 0 and N is connected to 1 volt. On both sides of the junction, positive potentials are there. P is at 0 potential and N is at 1 potential, 1 volt. So this makes the PN junction reverse biased. Same situation you can observe here in the JFET. Gate is at 0 potential, and everywhere at any point in the N-type channel, you could see a positive voltage. So the meaning is that when charge carriers are moving from source to drain, when there is some drain current flowing through the channel, a voltage drop will be developed along the length of the channel, which makes the gate source junction reverse biased. See here, we have not given any external voltage, not provided any external reverse bias voltage. Kani, because of this voltage drop, along the channel, it is making the gate source junction reverse biased. Externally, we have not given any reverse bias voltage, but internally, because of this drop, the junction is entering into reverse bias. The junction is entering into reverse bias. And if you observe, reverse bias effect is more towards drain end. This is 0 and this is 3. So reverse bias effect is more at the points which are nearer to the drain end. On N side, everywhere positive potential. So no doubt that this junction is reverse biased. But this effect of reverse bias, if you observe here, it is 1 plus 3 on the N side. So the effect of reverse bias is more towards the drain end. Therefore, depletion width will be penetration compared with the rest of the region. So this is the penetration of the depletion region into the channel. This is called wedge shaped depletion regions. These are called wedge shaped depletion regions. Wedge shaped depletion regions. Now we will come back to this figure. When the positive potential on the drain is further increased, then the charge carriers, when they are moving from source to drain, this movement generates a current called drain current. So when this current is flowing through the channel, potential drop is developed along the length of the channel, and this potential drop makes the gate source junction reverse biased. This potential drop along the channel makes the gate source junction reverse biased, and this reverse bias effect is more towards drain end. Therefore, penetration of the depletion region is more towards drain end, and the shape of the depletion regions are going to be called as wedge shaped depletion regions. So as we discussed in the previous case, instead of the drain current increasing linearly with VDS, the rate of flow of the charge carrier starts decreases. Because when the wedge-shaped depletion regions are formed, when depletion regions are widened because of the internal reverse bias effect, channel width of the channel is reduced and the channel resistance is increased. Therefore, the rate of flow of the charge carriers decreases. Therefore, instead of increase bending, so rate of flow of the drain current rate of flow of the charge carrier starts decreasing. Now, the third case, if you observe, further increased. The positive potential at the drain is further increased. 3 plus. 3 pluses are indicated it implies that more further the positive potential is increased. Now, at certain positive potential, if the positive potential is further increased, then what will happen? At one particular potential of VDS, these wedge-shaped regions, depletion regions, may come in contact. They may come in contact. So they may come in contact. Therefore, unlike the earlier case, what is that case? Here, if you observe, the depletion regions are widened uniformly throughout the junction, around the junction. The widening of the depletion region is uniform, and the channel is completely filled by the depletion region. That is why current has become zero at this situation. This situation is called pinch off, where current has become zero. But whereas here in this case, depletion regions are merged. They have come in contact. but channel width is not complete. Okay, so initially you may expect that charge carriers may not flow from source to drain, so current is 0. No, current will increase linearly with VDS for small potentials of VDS. When VDS is small, current should increase linearly. But as soon as we are increasing VDS, the channel width is decreasing, resistance of the channel is increasing. So slope of the channel decreases. And at one particular positive potential of VDS, when the wedge-shaped depletion regions are come in contact, the rate of flow of charge carriers becomes zero. I'm not saying that number of charge carriers. I'm saying rate of flow. Number of charge carriers. Okay. So here, therefore, when VDS we are increasing from 0 to VDS plus VDS plus VDS and plus VDS, rate of flow is getting decreased and becomes 0. It means the number of charge carriers. It means number of charge carriers. Number of charge carriers moving from source to drain, moving from source to drain becomes constant. So fixed number of charge carriers. The number of charge carriers which are moving from source to drain will be constant. Will become constant. That is why I have written here rate of flow is 0. What do you mean by rate of flow? Number of charge carriers moving from source to drain per unit time is constant every time. So therefore, it is 0. So therefore, at one particular voltage called of VDS, current remains constant. Current remains constant. The number of charge carriers from source to drain will be constant. So current, I'll take 5 more minutes. Current gets saturated. This is very, very important direct question for 10 marks. That is why I'm explaining very slowly. So current gets saturated. Now see here. The drain voltage at pinch off is referred to as VDS sat. What do you mean by pinch off? The drain voltage where these wedge-shaped depletion regions are coming in contact. So that is also called as pinch off. And the drain voltage where this pinch off is taking place is denoted with a VDS sat. So after that, even if you increase VDS, the transistor is said to be in saturation region and the drain current is independent of VDS. So drain current is independent of VDS. So once pinch off takes place, number of charge carriers will be fixed. So fixed number of charge carriers will be moving from source to drain. So therefore current becomes constant, independent of VDS. So this voltage we are saying that it is VDS sat. The drain voltage where current is becoming constant, the drain voltage where the wedge-shaped depletion regions are coming in contact, that is called VDS. సో ఎప్పుడైతే డిప్లీషన్ రీజియన్స్ కాంటాక్ట్ అవుతాయో దెన్ వీ సే దట్ pinch off has taken place. At this voltage onwards, current becomes constant. So this is called VDS sat. So then tarvata, even if you further increase voltage independent of VDS, it maintains that constant voltage. So why, how charge carriers will cross from source to drain? If channel is closed, you may get a doubt. So here there is an explanation given here. All of you observe here. If this is the channel length, see here, if this is the channel length, and see here, if this is the length of the depletion region which occupies the channel, this is the length of the depletion region which channel is not completely occupied here. Okay, so delta L is the length of the depletion region and L is the channel length. So delta L is very, very small compared with the length of the channel. So when delta L is very, very small compared with the length of the channel, the electric field in the channel remains constant. So if delta L is very, very small compared with L, then whatever the depletion regions, if you recollect the PN junction, this is the only conceptual topic we have in the 5th unit, remaining mathematical analysis only, the circuit diagrams and mathematical derivations. So this is very, very important to understand the characteristics of JFET. So if this is the depletion region, if you remember, a positive potential and a negative potential is developed and electric field will be developed around the depletion region. So here also, if you observe, the electric field will be developed around the depletion region, and this field is going to be constant. If the length of the depletion region is much smaller compared with the length of the channel, the electric field is going to be constant. If E is constant, the number of charge carriers, always the electrons will be moving in the direction opposite to the direction of the electric field. So when when the field is constant, the number of charge carriers which are moving from source to drain will become constant. The electrons which are moving opposite to the direction of E field, so the number of electrons moving from source to drain will become constant. So see here, this E field, this electric field is responsible for the charge carriers to cross this depletion region and enter into the drain side. So here, so electrons move through the N channel from source and they will be injected into the space charge region when they are subjected to the E field. So because of the electric field, they will be swept through into the drain contact area. So like that, the charge carriers will be moving from source to drain. So therefore, drain current is going to be constant. Once these wedge-shaped depletion regions come in contact, thereafter, drain current is going to be కాన్స్టెంట్. మీరు ఇదంతా ఎక్స్ప్లెనేషన్ ఎగ్జామ్లో రాయనక్కర్లేదు. సో ఈ పొటెన్షియల్ గురించి కూడా యూ నీడ్ నాట్ డిస్క్రైబ్ ఇన్ డీటెయిల్ అబౌట్ దిస్ పొటెన్షియల్ డిఫరెన్స్. 1 volt, 2 volt, 3 volt, like not required to describe in detail about why this wedge shaped depletion regions are getting formed. Only the statement you can write directly. You can write the statement. You can write directly the statement that, one second, I will show you. Just we will quickly read out this para. For a zero gate voltage and a small drain voltage. So for when VGS is 0 and small positive voltage, the current ID and VDS increases linearly. So the curve is going to be like this, increases linearly. As drain voltage increases, see, as drain voltage increases, gate to channel PN junction becomes reverse biased near the drain terminal, so that the space charge region extends further into the channel. So like that, if you just write the sentence that when VDS is increased, the gate source junctions becomes reverse biased. When VDS is increased, ఇక్కడ చూడండి, స్మాల్ పాజిటివ్ పొటెన్షియల్ అయితే డ్రైన్ కరెంట్, డ్రైన్ వోల్టేజ్ లీనియర్గా ఇంక్రీజ్ అవుతాయి. When this positive potential is further increased, this gate channel junctions will become reverse biased, and depletion regions will be, region is not uniform, because reverse bias effect is more at the points which are more towards drain end. And this type of shape of the depletion regions are called wedge shaped depletion regions. So if you when wedge shaped depletion regions are formed, rate of flow in the charge carrier starts decreasing and slope of the curve decreases. And if you further increase VDS at one particular voltage called VDS sat, these two depletion regions come in contact, and here rate of flow of charge carriers becomes 0. It means number of charge carriers moving from source to drain will be constant. So therefore, current will become constant. And in this situation, channel is not completely occupied by the depletion regions. Only delta L of the channel is occupied by the depletion region. So depletion region length is very, very small compared with the length of the channel. Therefore, the electric field around this depletion region will be constant, and which makes the number of charge carriers moving from source to drain will be constant. So current will become constant. So these are the characteristics of the JFET. Tomorrow we will draw the characteristic curves. In the tomorrow's class, we will draw the characteristic curves, ID with a function of VGS and VDS. Here we have seen separately the effect of VDS and VGS. Now in the next class, combining these two, we will draw the characteristics of the JFET And this is today's class. Coming to the, one second. Okay, so lab records, we don't know whether they provide lab records or not. Better you start writing in A4 size papers, lab records. So lab experiments and A4 size paper lo rayandi. So these are the list of experiments. All of you see here the list of experiments. And if you observe the third and fourth చూస్తే కనుక half wave separate experiment లాగా ఉంది, full wave separate లాగా ఉంది. And we have not done half wave rectifier with filter. So with filter చేయలేదు. But as per but you need to write both half wave and full wave in your record. So half wave rectifier with capacitor filter. We will write only half wave rectifier with capacitor filter. So మనం ఏంటంటే థర్డ్ ఎక్స్పెరిమెంట్ హాఫ్ వేవ్ రెక్టిఫైయర్ వితౌట్ ఫిల్టర్ సర్క్యూట్ డయాగ్రామ్ గీయాలి. అండ్ నెక్స్ట్ హాఫ్ వేవ్ రెక్టిఫైయర్ with only capacitor filter, with capacitor filter, with capacitor, with capacitor filter. ఓకే, సో మీకు ఎగ్జామ్లో హాఫ్ వేవ్ రెక్టిఫైయర్ విత్ ఫిల్టర్ కూడా ఇవ్వచ్చు, చేయకపోయినా కూడా ప్రొసీజర్ ఏం కాబట్టి హాఫ్ వేవ్ రెక్టిఫైయర్ వితౌట్ ఫిల్టర్ అడిగినా చేయాలి, విత్ ఫిల్టర్ అడిగినా కూడా చేయాలి. అండ్ మరి అబ్జర్వేషన్స్ ఎక్కడి నుంచి వస్తాయి అంటే I will show you in you have ACES and extra periods on Friday, right? So on this Friday I will try to show you how to simulate. So simulation, using simulation software, we will do using simulation software, we will perform the half wave rectifier with the capacitor filter, and whichever results we observe in that simulation, we will write those observations in the lab record. And we will be performing two experiments using simulation. One is half wave rectifier and the second one is CE amplifier. So I will show you these two experiments in the simulation software. There is a software called Multisim. By Friday, if you want, you can get it site on the Get Into PC ani. Get Into PC. I don't know exact spelling of this. Get in number 2 lekapothe TO2 na telidu. So you can log into that Get Into PC. Trial versions will be there. You can download them. Multisim. So whoever is having the computers with internet, they can download. Otherwise also not a problem. I will show you the simulation. I will generate the results, and the same results I will send it to you. You can just take them, print out of them, and you can get it attached at the end of the experiments. So half wave rectifier with, we have completed till 6th వరకు కంప్లీట్ చేసాం. 6th one and BJT biasing circuits. All of you, మీకు మాన్యువల్లో అన్ని బయాసింగ్ సర్క్యూట్స్ లేవనుకుంటున్నాను. I have not gone through the manual which was provided to you recently, but in the earlier manual only fixed self bias is there, but you need to write all the 3 biasing circuits. మీకు ఎట్లా అయితే ఫిక్స్డ్ బయాస్ కి ప్రొసీజర్ ఇచ్చారో, ఇన్ ఏ సిమిలర్ వే యూ నీడ్ టు రైట్ ది ప్రొసీజర్, సర్క్యూట్ డయాగ్రామ్ అండ్ క్యాలిక్యులేషన్స్. సో బయాసింగ్, you need to write all the 3 biasing circuits. So fixed biasing circuit, collector to base, all the three biasing circuits you need to write in your record. Though they are not there in the lab manual, all the three you need to write in the record. So first, design calculations. You need to write the design calculations. Very soon we may ask you to, you must be prepared with the lab record. You be prepared with writing with the lab record, because lab internals are going to conduct in very soon. Whether it is offline or online, we don't know. But we just, I got the information unofficially that lab internals are going to be there. So design calculations, circuit diagram, procedure. So like this, you can draw the margins in A4 papers, proper margins తో నీట్గా రాయండి. And you need to there are calculations. You need to calculate resistance. You need to calculate the dynamic and static resistance. Note down చేసుకోండి ఎవరైనా. Dynamic resistance as well as static resistance are not required. The static resistance is not required. Just we will see measurement of static and dynamic, both are there in the experiment itself. It is given, it is mentioned. So you need to calculate the dynamic resistance, and static resistance. So once you obtain this VI characteristic curve, you need to select 2 points. For dynamic, అదే స్టాటిక్ అయితే ఒక పాయింట్. డోంట్ టేక్ పాయింట్స్ అరౌండ్ దిస్ నీ, ఇక్కడ తీసుకోకూడదు. యూ నీడ్ టు సెలెక్ట్ ది పాయింట్స్ బియాండ్ ది నీ ఆఫ్ ది కర్వ్, నీ పోర్షన్ ఆఫ్ ది కర్వ్. సో V by I is static, delta V by delta I is the dynamic. So you need to calculate these two resistances for diodes, for all the 3 diodes, for all the 3 diodes, silicon, germanium, xenon. In forward bias and in reverse bias. Forward lo calculate cheyali, reverse lo calculate cheyali, 3 diodes ki calculate cheyali. These are the calculations pertaining to the first experiment. Second experiment, percentage line regulation you need to calculate, and percentage load regulation you need to calculate. So in on this Friday, I will explain how to calculate the percentage line and load regulation. These are the calculations related to the second experiment. And coming to the third experiment, third, half wave rectifier. నాకు చెప్పలేదు, I don't have the information. You should not tell, no one should tell that I don't have information. So I'm already writing here. All of you please note down this calculations part. Coming to the half wave rectifier, draw the tabular column. All of you, whatever the current, AC current you are measuring from the meter, it is not simply IAC. You write IAC RMS, IDC, VAC RMS, VDC. And here ripple factor in terms of the currents ratio, and another column in terms of the voltages. So IAC RMS by IDC and VAC RMS by V for the ripple factor. Coming to the half wave rectifier with capacitor filter, you need to note down IAC RMS, IDC, VAC RMS, VDC, ripple factor practical, and ripple factor theoretical. Here also you should write theoretical and practical. Ikkada kuda meeru theoretical and practical. Practical means whatever, theoretical means whatever the ripple factor value we have derived in the class, that will become the theoretical. 1.21 for half wave rectifier. So theoretical. So practical ripple factor ante VAC RMS by VDC and IAC RMS by IDC. So 2 columns. Again in this, 2 columns, one for current, using current, one for using voltages. And theoretical, we have derived the expression for the ripple factor. What is the ripple factor of half wave rectifier? With 1 by 4 root 3 FCRL. Sorry, 2 root 3 FCRL.
Excuse me, ma'am.
So yes.
Madam, everyone is asking me to
Yes.
convey this. Madam, can you explain this on Friday, as we have some extra time there?
మీరు ఇంకా ఫ్రైడే వరకు స్టార్ట్ చేయరా క్లాస్ రాయడం? So okay, you write the theoretical part, whatever is there. Leave 1 or 2 pages for calculations. Okay. So in every experiment we have the theoretical and practical calculations. Okay. Okay, then you can send me the attendance.
Yes, madam. I have noted already.
Okay. And on Thursday,
Ma'am, we have to write JFET, ma'am, experiment. 7th experiment.
JFET we will see. JFET చూద్దాం. ఫస్ట్ అయితే ఇవి రెండు చేయాలి. ఎందుకంటే మనకి సిలబస్ లో హాఫ్ వేవ్ వితౌట్ ఫిల్టర్, విత్ అండ్ వితౌట్ ఉంది కాబట్టి ఫస్ట్ వి విల్ పర్ఫార్మ్ దిస్ హాఫ్ వేవ్. నెక్స్ట్ యాంప్లిఫైయర్ ఒకటి కూడా చేయలేదు కాబట్టి అల్టిమేట్లీ ది అప్లికేషన్ ఆఫ్ ట్రాన్సిస్టర్ ఇస్ యాంప్లిఫైయర్ ఓన్లీ, రైట్? సో వి విల్ పర్ఫార్మ్ వాట్ ఈస్ యాంప్లిఫైయర్. ఆఫ్టర్ దట్ ఇఫ్ యూ గెట్ ఎనీ టైమ్, then we will see JFET. Okay. So don't write JFET now. Unless I tell, you need not write JFET. So these are the experiment. You can write the theory, everything. Observations are also there with you. And you can leave 1 page for theoretical and practical calculations. Okay. So in every experiment, we have to derive some parameters from the characteristic curves. So I will tell you on the Friday. Okay, then you can leave. If you have anyone is having doubt, they can ask. Remaining can leave.